Hello and welcome to part two of our chapter 9 lecture. Part two of this lecture continues on with our talk about stoichiometry. We're going to get into the idea of limiting reagents, excess reagents, and percent yield. And now, part two of stoichiometry. All right, everybody, welcome back here. Chapter 9, part 2 coming up. Continuation, obviously, of part 1. So, in part 1 of chapter 9, we talked about basic stoichiometry problems, and basic stoichiometry problems really do follow four sort of steps that we talked about mainly. Remember that the first thing you always want to do when you're doing anything with an equation, and especially with stoichiometry, is you want to make sure you always have a balanced equation. So remember that none of this works in terms of the calculation if you are not first starting with that balanced equation. So either if you have to write the equation, or if you're given an equation, you want to make sure that it's balanced. That is always where you want to start first. The other thing that you want to do next after you have that balanced equation is they typically will give you a piece of information in that particular problem, in that particular equation, and you want to get that piece of information into units of grams usually, and then you want to convert those grams to moles. So that's usually your second step, is to get everybody into those units of moles. Remember to do that in a basic stoichiometry problem. That is your molar mass from the periodic table, which again are the grams per mole that you get from, again, that number there on the bottom, right? And we go about four significant figures when we pull that off the periodic table. Once you have that in moles, the really reason why you need to do that is the third step in a basic stoichiometry problem, which is to use the mole to mole relationship. And that relationship, as we talked about, comes directly from the actual balanced equation, which is why step number 1 is really important to make sure that you do. So for example, here we have this made up equation. Remember that the stoichiometry comes from the balanced equation, and it's really nothing more than the actual coefficients that you see in the balanced equation. Remembering that, again, if you do not see a coefficient, it is not 0, but it does equal 1. This, as you might remember, is how we could get our relationships, like 2 moles of A reacts with 3 moles of B. And again, it's just the coefficients. We can also say 2 moles of A would get us produce 4 moles of C. We could also say, for example, 3 moles of B would also produce 4 moles of C. These are all stoichiometric equalities. They're all equal to each other. And as we talked about last time, they are not equal to each other in terms of 2 does not equal 3, but they're equal to each other, again, in terms of proportions of what you need for this reaction to take place. And because technically speaking, they are equalities, you could write 2 conversion factors for each of these guys. For example, this one, 2 moles of A over 3 moles of B, or 3 moles of B gives you 2 moles of A. So, and again, you could do that for each of these conversion factors down here. We could actually, in this example here, actually have 6 different conversion factors that we could get from the equation. And that really is what stoichiometry is. It's a conversion factor. And the difference is, instead of like going to a table and finding that conversion factor, we actually use the balanced equation to get the conversion factor. And that's because oftentimes in stoichiometry problems, we're given, let's say, information about A, but we really are interested in what is happening, for example, with C. So we need a way to convert from A to C. We use stoichiometry in the equation to do that. And that's really what stoichiometry is. So that's the third step, which is the mole-to-mole relationship from the balanced equation. And once again, that is the purpose of step number 2. So everything's in the proper units to cancel out in step number 3. Now, step number 4 is, after you do really the stoichiometry step, you will always be in moles. And Sometimes maybe that is the answer that you're looking for. That is the proper units that you want, but a lot of times it's not. So a lot of times you're looking for some other unit. And a lot of times at the end here, you may have to do 1 conversion, 2 conversions, whatever it may be. I would say in these sort of basic stoichiometry problems, like we're talking about in this chapter, a lot of times that last step is taking the moles back to grams. And again, on the back end here, we would use our molar mass one more time. And when I say one more time, we will not be using the same molar mass as we did in step number 2. We'd be using the molar mass for, for example, whatever we were looking to find. So those are the same 4 basic steps that you should perform in a basic stoichiometry problem. If you just follow those steps, you should end up at the right answer. We're going to now talk about sort of a variation, if you will, or a really more real life sort of example, I guess, in a sense of how reactions usually will take place. And this brings up the idea of limiting reagents. It's also sometimes called limiting reactants. I personally call it limiting reagents, but again, if you hear limiting reactants, it's the same sort of thing. And it's really the idea that no matter what happens in a chemical reaction, there's always going to be a reactant that gets used up first. So there will always be this reactant that gets used up first. And there will also be usually a reactant that you have pretty much plenty of. So when this reaction takes place, they do not sort of perfectly use up each of each other exactly. You don't use the same amount of both reactants, and each reactant usually have more than one and less of another. And the one that gets used up first is what's known as the limiting reagent. This one gets used up first, which means it gets completely used up and there's no more of it when it's all done the reaction. So why is that really important, the limiting reagent? It's really important because if you just think about a logical example, let's just say we were doing this very simple reaction of A plus B makes A and B. All right. And let's just say, for example, we figured out that A is our limiting reagent and B is we have plenty of. And as we'll talk about in a second, that's what's sometimes referred to as the excess reagent or the excess reactant. So in this particular reaction, the only way to make product is we got to basically put A and B together, right? So at some point as this reaction is taking place, I'm going to run out of A, which means there is absolutely at that point when we run out of A, which is our limiting reagent, there's absolutely no chance of making any more product because clearly in this very simplified example, I need an A and I need a B to make the product. And as soon as A runs out, there is no chance you're going to make any more product because you're missing half of what you need pretty much. So the importance of limiting reagents is it is always the limiting reagent that basically determines how much product you can make. So that's why when we do come across a limiting reagent type problem in chemistry, one of the main things that you definitely have to do is figure out which one is the limiting reagent. And that is because it is only the limiting reagent that's going to determine how much product we make. In this very simplified example of B, we have plenty of, which means we could still have B when the reaction's over, and we will still have some of B when the reaction's over, but we have no more of A in this example. So A is really the determining factor as to how much product that you can produce. So whenever you're trying to figure out how much product you should produce, which is sometimes referred to as a yield, you always want to do it based on the limiting reagents. So you may be asking in a basic stoichiometry problem like we did, say, in the first part of this lecture and in the previous video, how come we didn't worry about, for example, limiting reagents? And the answer is this: it is assumed that what they gave you in that problem. So if you remember, In those problems, perhaps we had a certain amount of reactants that we were given, and we would only be talking about reactants in this case. If we have a problem where they just gave us, say, 5 grams of A, and that was the only piece of information that was given to us, it is assumed in those type of problems that the A, for example, is the limiting reagent, and the other guy would be the excess reagent. So when you're only given one piece of information about the reactants, it's assumed that that is probably your limiting reagent, and the other reactants would actually be your excess reagent. So we didn't have to worry about those in sort of part 1 of this lecture because it wasn't a limiting reagent situation. So that brings up a really good point of, how do I know it's a limiting reagent situation? Well, first off, let's just officially here talk about the other sort of reagent or reactant that's present, which is the excess reactant, our excess reagent. And the excess reagent is the one that you have plenty of, and you actually will have some left over when the reaction is done. So, a real life example, I think they still sell it this way. I'm going to try to remember which way they do it, but I think if you buy like hot dogs, for example, in the market, and you buy some hot dog buns, maybe you're going to have a barbecue, you're going to make some hot dogs. Sounds pretty good right about now. But in order to make completed hot dogs with a hot dog and a bun, they typically, I think, used to sell hot dogs in a package of 10, and they would sell like the buns, for example, in a package of 8, which means, for example, if you had a package of 10 hot dogs and only 8 buns, that means if you wanted to make your products of a hot dog and a hot dog bun, the best you're going to do is, since you only have 8 buns, is you're only going to be able to make 8 of them. And that would mean that the hot dog buns in my example here is our limiting reagent. And the hot dogs themselves are actually my excess reagent. So as I mentioned before, we would know in this case, we could only make 8 units pretty much. By the way, that would also require us to use up 8 hot dogs, which means we would actually have 2 hot dogs left over. And that's very common sort of things that you could find out in limiting reagent problems is how much product you would make based on the limiting reagent. You could also figure out how much of that excess reagent you would still have left over at that point. So as I was mentioning before, how do you know if it's a sort of basic stoichiometry problem? It's a limiting reagent sort of stoichiometry problem. Well, the deal is this: in a basic stoichiometry problem, where you would follow those 4 steps that we talked about, which again is balance your equation, convert to moles, do your mole to mole relationship, and obviously moles to some other unit. You're basically just given one piece of information, right? And you basically have one piece of information that you can convert to moles. For example, like I started with 5 grams of A, and that's the only piece of information I'm given. Now, how do I know it's a limiting reagent type problem? Well, you are given enough information for your reactants that you basically can convert to moles. So if you see in a problem, for example, if we just take that A plus B example that we sort of been using here as just a basic example, if you are told you are reacting 5 grams of A with 5 grams of B, you would be able to convert those grams of each reactant into moles. And that is the key to know, oh, this is a limiting reagent problem. So if you ever come across a stoichiometry problem where they give you enough information, and in this case, grams to moles, for example, or really any other way, we're going to talk about gas stoichiometry, solution stoichiometry. But the key is that you have enough information about both reactants, for example, that you have a way to, just from the information given to you, get those numbers into moles. Then you know it's a limiting reagent problem. Now, in a basic problem, you have enough information only to get one reactant into moles.
So that's why it's a basic problem. You don't have to worry about limiting reagents. But if you see, yes, in fact, I could get both pieces of information they gave me into moles, it is a limiting reagent problem. So what is the difference in terms of sort of how you would approach a limiting reagent problem versus a basic stoichiometry problem? The good news is one approach is you pretty much can just do the same steps. So you would balance your equation, you would convert to moles, you would do your mole to mole relationship, you would take your moles to some other unit. So what is the difference? Well, right around here, for example, right around this step, you need to figure out the limiting reagent. Or not the LB there, that would be Long Beach. Let's try not Long Beach. Let's try the limiting reagent, perhaps. All right, let's try that there. The limiting reagent. There you go. Maybe it's close to Long Beach. Who knows? So figure out the limiting reagent here, and once you do, you would then do the rest of the steps with the limiting reagent. So that's also a really important difference. Right after that second step, you could do a calculation to figure out which one's the limiting reagent. And then you should always use the limiting reagent to figure out how much product that you would produce. So that's the main difference. I'm going to be truthfully honest with you. There's many approaches and, 3 or so, 4 maybe different ways that you could actually do limiting reagent problems. I'm going to show you probably 2 ways. I think one way like in the book and another way to do it. And again, you could choose kind of either way to do it. But just so you know, there are a few different ways that you can approach limiting reagent problems. And we might talk about a couple of different ones here. But that's the real main reason it's difference. Again, if you see you have enough information to get the moles for everybody, limiting reagent problem, need to figure out the limiting reagent. Limiting reagent is the one that determines how much product you produce. So if we look at just another kind of basic example here, we got women workout and men workout people here. And to make workout buddies here, we need one of each. So obviously we would need 1 and 1 to make that one, perhaps. We'll need another one here and another one here to make that. We would need this one here and this one here to make this product, which means here, if we kind of get rid of everything we use, I am out over here of the men workout guys, which means that these guys in my example here would be our limiting reagent. I actually do have some left over here of the women workout people. And if we look at it here, we could actually figure out how much is left over. We have 1 and we have 2. So this would be our excess. And again, we could figure out how much of our excess is left over. It is our limiting reagent, as you can see here. Because we only have 3 guys, that's as much product as we can make. So once again, it is always the limiting that determines how much product that you can make. All right, so let's take a look at an example here and sort of go through some of these steps here and really sort of identify how to approach these type of problems. So first off, we'll take a look at this equation. And regardless of what type of stoichiometry problem it is, basic stoichiometry or limiting reagent stoichiometry, the first 2 steps pretty much in all stoichiometry approaches or problems are pretty much the same. So the first thing that we want is we want to balance an equation. So here we do have an equation and it is balanced. So we're good to go on that. The next thing we want to do is convert to moles. So in this example, we're going to assume that we're starting with 4 moles of S and 20 moles of F2. So I'm just going to rewrite this equation down here. So in this case here, we are starting with 4 moles of our sulfur and 20 moles of our F plus F2, slight plus, I suppose. And we really want to figure out eventually how many moles of our SF6 are there. Okay. So at this point, step number 1 is done for us. Step number 2, which is whatever they give us, convert to moles, also done for us. Now, how do I know this is a limiting reagent problem? Well, it's pretty straightforward in this example. I have moles of one reactant and I have moles of the second reactant. Although I didn't need to convert them to moles, which I could have done if I were given grams, because I could take grams to moles using the molar mass. But that right there is the big key of this is a limiting reagent problem. We have the moles of each of our starting reactants, and that is the key that, hey, I need to figure out which one's the limiting reagent to do that. So we have now balanced the equation. It's already in moles, or we converted our starting guys into moles. We then want to, in this case, because we do know it is a limiting reagent situation, we want to figure out a limiting reagent situation. So I'm going to show you first one method to do it, which I think is a pretty good method. And then we'll talk about perhaps another method in just a second. So to figure out which one is the limiting reagent in terms of our 2 reactants, we're just going to do a basic stoichiometry problem where we're going to figure out, in this case, if I want to use up all of my sulfur, how much fluorine would I need? So we're just going to do this little calculation here to figure out which one is the limiting reagent by basically doing that. So I'm going to take the moles of sulfur that I'm starting with, which is 4 moles. I'm going to do the mole to mole relationship between the 2 reactants. So once again, we could see for every 1 mole of sulfur from the equation, we get 3 moles of fluorine. So that's just a basic stoichiometry relationship between the 2 reactants, and we're going to use that. So I'm going to put 1 mole of sulfur on the bottom from the equation, 3 moles of F2 up on top. The moles of S will cancel, and that will tell me 12 moles of F2 is needed. So I'm basically figuring out in this little calculation how many moles of F2 is needed to completely use up the moles of sulfur. So basically what you're doing is figuring out, okay, I got 2 reactants. If I want to use up one completely gone, how much of the other one do I need? So what do I do with this piece of information? This is where our starting is really important. We're going to compare. And we're going to compare between how much is needed of the F2 to how much I am starting with. And in this case, I need 12 moles of F2. I am starting with, in this problem, 20 moles of F2. Do I have enough? And I'm hoping you're shaking your head yes, or nodding your head, I guess yes would be a better way of doing that. You do have enough is the answer. So the answer is yes, I have enough. So what does that mean? So when I go to compare this, I need 12 moles of fluorine in this example to use up all my sulfur. I have 20. I have enough. What that tells you is, in this example, the fluorine is the excess reagent. And one of the nice things about limiting reagents is if you can figure out which one's the limiting reagent, or if you can figure out which one's the excess reagent, by default, the other reactant is the opposite. And that would mean in this case that my sulfur would be my limiting reagent. So by doing this small little calculation, I could very easily figure out which one's my excess reagent and which one is my limiting reagent. And by our calculation here, we see that is the sulfur. Now, doesn't matter which reactant you choose to do this calculation with. The answer is it doesn't. So for example, on this first one, we wanted to use up sulfur and we want to know how much fluorine was needed. We could have done this exact same calculation, for example. And we could have said, hey, if I want to use up all of my fluorine, how much sulfur is needed? So we could have picked either reactant here. And let's just say we did the opposite calculation. So I'm going to start with my 20 moles of fluorine. I'm going to use my same mole to mole relationship from the equation between the two. I'm going to use it in the opposite way. The 3 moles of fluorine will go on the bottom, and the 1 mole of sulfur would go up on top. Moles of fluorine would cancel, basically giving us 20 divided by 3, which is 6.67 moles. 6.67 moles of sulfur is needed. So let's just say I chose the other reactant. I did this calculation. I once again would compare between both the moles of sulfur needed, which in this case is 6.67, and the moles of sulfur I'm starting with, which in this case is actually 4. And what we see here is the same result, not the same numbers, but the same result. In this case, when I compare these two numbers, I do not have enough. And in this situation, if I were to have picked the fluorine to be used up and I did sulfur, how much I needed, I would not have enough. And that would tell me the exact same thing. Because I do not have enough, that means still the sulfur is my limiting reagent and the fluorine would be my excess. So in this method, to figure out the limiting reagent, you don't have to do both reactants. You would just choose one reactant, and you want to figure out how much of the other reactant you need to put in there to use it all up. And if you have enough, then that reactant is the excess reagent. And if you compare between how much you need and how much you started with, and you do not have enough, then that guy's going to be your limiting reagent. Okay, so once again here, don't have to do both of those calculations. Can just choose one. And regardless of which one we chose, we saw that, again here, the sulfur is our limiting reagent. So what that means is we would then move on to step number 3, using our limiting reagent, and now do our mole to mole relationship between the limiting reagent and the product. So in this case, we will now do our limiting reagent, and we're going to go back and actually start with the starting amount of it. So we're not going to use any of these numbers here in these calculations. These are just 2 calculations, or if you just did one calculation to figure out which one's the limiting reagent. It's important when you go back to sort of the third step that you actually use the starting amount of your limiting reagent. And that starting amount of our limiting reagent was 4 moles of sulfur. We now can do our mole to mole relationship between sulfur and SF6. And in this case, it is 4 moles of sulfur gives us 1 mole of SF6. And it's not, it is actually, I'm sorry, I wrote the wrong number there. It is 1-to-1 from the equation. That would be much better. Try that again. It is 1 mole of sulfur is 1 mole of our product. So I got a lot on the page there. We're just going to clear that out so we can see that relationship. So here, what we're looking at here is, we are now looking to figure out how much product. So it is a 1-to-1 relationship between those two. 1 mole of sulfur gives us 1 mole of SF6. There we go. I scribbled too high up here to see the number. That gives us here that we would produce 4 moles of SF6 in this case. Moles of sulfur will cancel. And this right here would be our theoretical yield. And it would be in moles. We could do step number 4, which would be our moles to grams if we were interested in it. But in this case, we're just going to stop at moles. So that is one approach. Again, the same 4 steps. We just do that additional calculation to figure out which one is the limiting reagent. And then we could do it at that point. Now, let's take a look at another approach here. And let me rewrite the equation here. S and F2. And 3 here. And once again, we are starting with 4 moles of this guy, and I believe 20 moles here of this one. So another approach to these problems is you basically just do 2 separate stoichiometry calculations from each reactant to the product to figure out how much each one produces. So the sort of second approach, different than the one we just did, is we will take each reactant individually. And by the way, we still know it's a limiting reagent problem because we do have moles of each of our starting material here. So we do have moles, or we're able to get the moles of each of these. So we will start with sulfur, and sulfur would go 4 moles of sulfur, which is what we're starting with. We would do our mole to mole relationship between the sulfur and our product. And once again, that is a 1 mole of sulfur equals 1 mole of SF6, gives us 1 mole of sulfur and 1 mole of SF6. That means here we will produce 4 moles of SF6 if we started with sulfur. We would then go back and start with fluorine, and we would start with the 20 moles of fluorine. We would do the mole to mole relationship between fluorine and our product, which in this case is a 3-to-1 relationship. So 3 moles of fluorine gives us 1 mole of SF6. So doing the exact same calculation here, 3 moles of fluorine and 1 mole of SF6 gives us 20 divided by 3 gives us our 6.67 moles of SF6. I'll squeeze it in there. So in the second approach here, what you do is you do a individual calculation between each reactant to the product of interest. And what you're going to then do is compare. Now, at this point, I did stop in moles. You could go all the way to grams and figure out how many grams of each one. Again, we use the molar mass here of SF6 to do so. But we would compare, and whichever one is the smallest would be both your limiting reagent and your theoretical yield. So let us take a look at that. Well, when comparing these two answers, it is obviously here 4 is our smallest, which means this would be the wrong answer. So we'll cross it out. This would be our theoretical yield in moles. And once again, you could convert to grams at this point. And that would also mean that sulfur was our limiting reagent. By the way, that would also mean that this guy would be our excess reagent. And that's the second approach that you could also do in this type of situation. Just 2 simple 4-step basic stoichiometry problems from each reactant to the product of interest, and compare how much each reactant makes of the same product. So it's got to be the same product that you go to, because you could have multiple products. So you want to make sure you go to the same product. Compare how much of the same product each of the reactants make individually, and whichever one makes the smallest number is both, that reagent would be your limiting reagent, and that would also be your theoretical yield. As you can see, both methods give you the exact same answer. We got 4 moles of SF6. We also saw in both cases the sulfur is the limiting. That is, again, a second approach. And I think that might be the approach in your book, the way it's taught. So if you like that approach better, you could do that. If you like the other approach better, you could do that as well. One of the benefits, perhaps, of the first approach that I showed you is, let's say, for example, we wanted to figure out, that's all not going away. We want to figure out how much of the excess reagents left over. So how much of the excess reagents left over is a very common question that is sometimes asked. What I'm going to do, I think, is erase some of this so I got somewhere to write. So let's just say, in addition to the original problem of we want to figure out how much product we're producing, we did want to answer that question of, how much of that excess reagent would be left over in this particular case. So if we go back to our first method here that I showed you, we can answer that question pretty quickly. And what I mean by that is, when we did our limiting reagent calculation to figure out which one's the limiting reagent, we figured out that the fluorine was the excess reagent. And we also figured out in that calculation, I need 12 moles of it, which means if I wanted to figure out how much of that excess reagent is left over, I would take the 20 moles that I started with. Because I did this calculation to figure out which one's the limiting reagent, I already know that I need 12 moles of it is needed. And that would tell me that I would have, I'm going to try it without the calculator here, 8 moles of my F2 in this case left over. And that's my excess reagent, which I also could convert to grams if I use the molar mass of fluorine to do so. So one of the benefits of sort of doing the first approach here is you might actually have the calculation already done for you to figure out how much of that excess reagent is left over, which again is a very common sort of question that's asked in these type of problems. The downside to, say, this calculation or this approach to limiting reagents is, although it might seem easier, and it may be easier to figure out, what your theoretical yield is and stuff like that, if you were asked that question of how much of your excess reagent is left over, after you did these calculations, you would then need to go back and do that calculation that we did previously, that, there's 20 moles of fluorine I'm starting with. I'm sorry, you would actually have to do the first calculation. You would have to go back and go, okay, my limiting reagent is 4 moles of sulfur. To use up all the sulfur with the fluorine, I again would have to do that and this, and then redo this calculation here, which you would have had to do perhaps anyways. So, it's not necessarily a big downside, because you could go back and do this calculation pretty easily anyways, but you would have to kind of go back and do that calculation. Now, if you did it the first way, you might actually have that calculation done for you. By the way, if you happen to have chose this to do your calculation, you would still need to go back and do that for the excess reagent problem. So, either way is a valid method. Again, whichever method you like better or works better for you, use it. There's also another way you could do these problems as well. So there's multiple ways you could kind of do these problems, but these are the two sort of common ways. And I would say nowadays, a lot of books, like I think yours, sort of shows this way here, where you just kind of do 2 separate calculations and figure out how much of your product you would produce, whichever one's the smallest. Again, the only thing with that is you might have to go back and do a little extra calculations for the excess reagent, which you might avoid or might have already done if you did the first approach. Again, I don't personally have a preference how you do it, as long as you choose the legitimate way, one of these 2 ways to do these type of problems. try it both ways, and again, use whichever way that you kind of like the best. All right, let's continue on here and take a look. So why don't you give this a try? You have 15 grams of nitrogen gas is mixed with 85.5 grams of hydrogen gas. What is the mass of ammonia that is formed? I'm going to give you some numbers that might be helpful for you. Nitrogen is 1401 on the periodic table. Hydrogen is 1.008 on the periodic table. And believe it or not, I think that's all you need. So again, follow those steps to figure out, is it a limiting reagent problem or not, and see what you come up with. Okay, so hopefully you're working your way towards the answer or have the answer here before you hit play. But let's take a look. Regardless, honestly, as we just talked about, a couple different approaches that you could do to these type of problems, or any stoichiometry problem, really the first two steps are always the same, which is we do need a balanced equation, which we do not have in this case. So let's start with that. Nitrogen gas is how nitrogen normally comes, and hopefully you remembered it is a diatomic molecule, right? So that's N2, not N by itself, is mixed with hydrogen gas, which is another diatomic molecule, which is H2, to form ammonia, which is our friend NH3. So once again here, we want to make sure that we get the proper formulas down, regardless of the whole balancing thing. But of course, as we know, we don't want to do anything unless it's balanced. So now that we do have the formulas down, we need to do some balancing. And I'm going to throw a 2 there and maybe a 3 there. And I think at that point we are good. We are balanced. So check it off. Secondly, we want to take whatever they give us and convert to moles, which in this particular case, I got grams, which means I do need to convert to moles. So I do have 15.5 grams of nitrogen, and I have 85.5 grams of hydrogen. So what I know is I have grams, and I can get to moles of nitrogen by using the molar mass. So I could definitely do that. I have grams of hydrogen, which means I could get to moles by using the molar mass to do so. That means that technically speaking, I could get to the moles of my nitrogen. I could get to the moles of my hydrogen. And that right there tells you this is a limiting reagent problem. So that right there, because I am given enough information about both reactants that I could actually get to moles, that means that this is going to be a limiting reagent problem. And that means that before I do that, though, I will have to convert to moles, but I also need to figure out the limiting reagent. So that is, again, the key to know that this is a limiting reagent problem. So we're going to need some molar masses here to convert those guys into moles. So nitrogen is 2 times 1401 from the periodic table. Going to give us there 28 and some change, looks like 2802. Hydrogen is 2 times 1.008 grams per mole. Again, from the periodic table, the molar mass, 2.016 grams per mole is our molar mass there for hydrogen. Remember, we're going to use the molar mass to convert everybody into moles. So that's the second thing that we want to do, really. We already just did our first thing. Second thing here, we're going to convert to moles. So I'm going to take my 15.5 grams of nitrogen, going to use the molar mass here from the periodic table, and that's going to give me a 2802 grams per mole, making sure I set it up sort of dimensional analysis so I can see the units canceling. We got 15.5 divided by 2802, going to give us a 0.55, we'll call it 3 moles of nitrogen. We're going to do the exact same thing here for our, I feel like I missed the first part there. Line them up a little better, maybe. Give the old college try here. 5. There you go. We're going to do the same calculation here, though, for hydrogen. So 85.5 grams of hydrogen using the molar mass there of hydrogen. 1.008 grams per mole of hydrogen. Going to give us 84.8 moles of hydrogen. So it's also important to remember that when you do these and you convert these grams into moles, you know, it might not hurt to put a little label on them that, hey, this is like my starting amount of each of these guys. All right. So now that I have converted it into moles and I know it's a limiting reagent problem, it is time to figure out the limiting reagent. So I'm going to do the method where I'm going to choose one of the reactants and figure out how much of the other reactant I would need to put in there to convert it into, or to use it completely up. I also see that I did use the wrong number there. Thank you for yelling at the screen. I heard you. And obviously I want to use the proper molar mass here, right? There you go. All right, take 2. I know I could probably cut it out, but I'll leave it in just to remind everybody. Yeah, sometimes mistakes happen. So 2.016 is actually the proper molar mass there for H2. So let's do that. 85.5. Thank you for politely yelling at the screen, and that's to allow that you woke up any neighbors. Hopefully 42.4 moles of hydrogen. That looks a little bit better. All right, so now that I got the right molar mass in there, coming back to this, we're going to do, again, a calculation here. And the goal of this calculation is to figure out which one's the limiting reagent. And really what we're going to do is go, I want to use up completely one of my reactants. How much of the other one do I need? So in this case, I'm going to try to figure out how much hydrogen is needed. So that means that I'm going to use up all my nitrogen. How much hydrogen do I need to throw in there? We're going to start with my nitrogen, which is 0.553 moles of nitrogen. We're going to do a mole to mole relationship between our two reactants. So again, from the equation, we could see that for every 1 mole of nitrogen, we have 3 moles of hydrogen. So using that, and again, this is the calculation that's going to allow us to figure out the limiting reagent. We have 1 mole of nitrogen, 3 moles of hydrogen. Moles of nitrogen are going to cancel, and that is going to get us a 0.553 times 3. Going to give us a 1.6. We'll call it 6 moles of H2 is needed. So again, this is the small little calculation to figure out which one's the limiting reagent. So how do we officially figure it out? Well, we just calculated in this calculation how much of my hydrogen is needed. We then want to compare it to how much of the hydrogen we started with. And the goal here is to see, do we have enough? And the answer looks like it. We're starting with 42 moles or so of hydrogen. To use up all of our nitrogen, we would only need 1.66. So we do have enough when we compare those two. So again, when we compare what we need to what we are starting with, we do have enough. So that tells us that in this example, the hydrogen is our excess reagent. The nitrogen is our limiting reagent. And again, that's the main purpose of that calculation. Now that I know which one's my limiting reagent, I could just kick back into the normal stoichiometry steps, which is now I could do the mole to our products. And in this case, we could see from the equation that since our limiting reagent is nitrogen and our product is ammonia, we could see that it is a 1 to 2 relationship between those two. So we could see that for every 1 mole of nitrogen, we get 2 moles of NH3. Now, again, it's important to make sure that we go back to the starting amount of our limiting reagent to figure out how much product. So again, this calculation for the most part is just used to figure out which was the limiting reagent. We want to make sure we go back to our starting amount here of our limiting reagent, and that's going to give me 0.553 moles of N2. Using the relationship that we just see there, 2 moles of NH3 up on top, 1 mole of N2 on the bottom. Those are going to cancel, and that will get me my 0.553 times 2. And that's going to give me 1.106 moles of NH3 in this case. By the way, this would be our theoretical yield in moles if that's what we're looking for. But we're not looking for moles. We're actually looking for grams. So we do have to do the fourth step, which is convert our moles into grams. So we are going to need the molar mass, but at this point, we do need the molar mass of NH3. So we're going to do the molar mass here of NH3. Just going to kind of clear out some things here. There we go. We'll do it up here, I think. There we go. All right, so NH3 from the periodic table, we have 1 nitrogen at 1401. We have 3 hydrogens at 1.008. So 14.01 plus 3 times 1.008. Going to give us 1703 grams per mole. And that's what we're going to use here on our final kind of fourth step. We're going to do 17.03 grams per mole of NH3. So that times our original number there that we had, looks like 18.8 grams of NH3 would be how much product we would produce. Once again, this would be our theoretical yield. Yield in grams, and also, by the way, our theoretical yield here in moles. So again, the same 4 basic steps, except that we recognize that it is a limiting reagent problem, which means we do need to take that extra step of figuring out which one's limiting reagent. Now, it wasn't asked in this particular problem, but if we did want to figure out how much of our excess reagent is left over, we could do that. So let's take a look. Now, if we want to figure out how much of our excess reagent is left over, we know hydrogen here was our excess reagent. And that means that we know from our calculation, we did get lucky. We did the right calculation in a sense. We know that we started with here of our excess, 42.4 moles of it for our H2, which is our excess. We know from our calculation we needed just 1.66 moles was needed, and we could subtract, and that would tell us that we had 42.4 minus 1.66 gives us 40.7 moles of H2 left over, which if we then multiplied by the molar mass of H2, 2.016 grams per mole, which is the molar mass from the periodic table, we would have something like 82.1 grams of it left over. And again, we started with 85 grams. So in this case, we use just roughly 3.4 grams of it in this reaction. In terms of the nitrogen in this case, we would have used up all of the 15.5 grams of nitrogen because it's our limiting reagent. But in this case, because hydrogen is our excess, we could do this little calculation here to figure out how much of it would be left over. In this case, about 82 grams of it. We didn't use very much in this reaction, which is why, again, it's the excess reagent. By the way, when you are figuring out the excess reagent and limiting reagent, you do have to do it based on calculation. A very common misconception sometimes is when I convert my reactants into moles, for example, the limiting reagent will always be the smallest number, and that's not the case. So in order to properly figure out which one's the limiting reagent, it does need to be based on some type of calculation. Is not just the smallest sort of number, if you will, in terms of moles of reactants. Again, that's a very common misconception. So you can't just look at, for example, when we did step number 2 here, and we figured out the moles of each of our starting amounts. We can't just look at them and go, oh, nitrogen is a smaller number, so it's always going to be the limiting reagent. So it is based on the stoichiometry of the equation. You cannot just look at those two numbers and go, that's small, that's the limiting reagent. It may not always be that case. You may actually have a case where you actually have the smaller number of moles, but it's actually the excess reagent. So don't fall into that trap, which is a very common trap. People just go to that step and go, okay, small, that's my limiting. I don't have to do anything else. You do have to do some type of calculation to determine which one's the limiting reagent. All right, let's take a look at a few more examples here to make sure this is all hopefully falling into place here. So why don't we try this one here? We're going 6.83 grams of iron are allowed to react with 9.34 grams of our friend sulfur. Which of the two is the limiting reagent, and how much of the iron 2 sulfide would be produced? Some information that might be helpful. Iron, I think it's still 5585 on the periodic table. And sulfur, how about a 3207? Seems like a good number. Let's try it. All right, so take some time here again. Clearly, I'm thinking it's a limiting reagent problem, so make sure you go through it and figure out how much product that you would produce. Okay, let's take a look. First off, regardless, whatever method we're doing, we want a balanced equation. We got that, so that's good. We also see that we are given 6.83 grams of iron. We're also given 9.34 grams of sulfur. That is the information about two reactants, both of which I have the capabilities of converting into moles. So the answer is, if you're not sure, this is definitely a limiting reagent type problem because I have the ability to turn the information about both reactants into moles. So I do know somewhere I have to do that sort of step there, figure out which one's the limiting reagent. The second step that I want to do is convert to moles. So I'm going to take whatever they gave me and convert it to moles. So we'll do it up here, 6.83 grams of iron. Using the molar mass from the periodic table, we're going to convert those into moles, and that's going to give me 85 grams per mole of iron. That gives me punching my calculator correctly, that would help, I suppose. 6.83 divided by 5585, that's going to be a 0.122. We're going to stop at that too. Moles of iron. We're going to do similar calculation here for sulfur. We got 9.34 grams of sulfur. Using a molar mass from the periodic table, a little 3207 action. Up sulfur. We'll go 934 divided by 9.34, 3207. Going to go 0.291 moles of sulfur. Once again, I'm just going to relabel both of these as, excuse me, my starting amount of each of these. Now, because it is a limiting reagent problem, boom, I'm at the point where I need to figure out which one's the limiting reagent. So again, here, I'm just going to pick one of the reactants, and I'm going to try to figure out how much of the other reactant I would need to use it up. So Gonna erase some of my check marks, I think, here. There we go. So what I'm going to do, I think, is I'm going to pick just going to pick the iron. So what I'm going to want to do is figure out how much sulfur is needed basically to use up all of my iron. So I'm going to start with my starting amount of iron, 0.122 moles of iron. I'm going to do the mole-to-mole relationship between iron and sulfur, which is a 1-to-1 relationship. 1 mole of iron gives me 1 mole of sulfur. That is the stoichiometry from the balanced equation. So we're going to use that as a conversion factor. 1 mole of iron means I have 1 mole of sulfur. Moles of iron going to cancel, means 0.122 moles of sulfur is needed. So again, this calculation is basically figuring out how many moles of sulfur I would need to put in there to use up completely all of my iron. This is how I'm going to determine which one is my limiting reagent. I'm going to now compare, once again, the moles of sulfur that I need with the moles of sulfur that I'm starting with. And when I compare those two, I could see, do I have enough? So I need 0.122 moles. I am starting with 0.291 moles. I do have enough when I compare those two. And what that means is, because I have enough of the sulfur, that means that the sulfur in this case is my excess reagent. And by default, that would mean that the iron is my limiting reagent. So again, a reminder that once you determine which one's your limiting reagent or excess reagent, by default, the other reactant is the opposite. So like we did here, we were able to determine from our calculation that sulfur is the excess reagent. And that means by default, iron would be our limiting reagent. By the way, if we did the other calculation, which you could do, and you don't have to do them both, but you could have figured out how much iron you would need to use up all of the sulfur. And what you should find when you do that is the amount of iron that you need should be more than what you started with. And that would tell you it's a limiting reagent. So again, you don't have to do both. Since we did this one calculation here, that's enough for us to know which one's the limiting reagent. But you could have done, again, the opposite calculation as well. Because it's the limiting reagent, that is what we want to continue with. Now we're ready to figure out our product by doing our mole-to-mole relationship, once again, using our limiting reagent to do so. So we're going to go again back to our limiting reagent and the starting amount of our limiting reagent. And we're going to go 0.122 moles of iron. We're now going to do the mole-to-mole relationship between iron, which is our limiting reagent, and our iron 2 sulfide, which is our product. And we can see in this equation, stoichiometry is pretty easy. 1 mole of iron will give us 1 mole of our iron 2 sulfide. So that's what we're going to use here. 1 mole of iron 2 sulfide gives us 1 mole of iron. Moles of iron cancel. I can still do this math, 0.122 moles of iron. At this point, we're interested in how many grams, right? So usually when they say mass, that is the indication that you want grams. And we do want the molar mass of iron 2 sulfide to do that. So that's pretty easy. We're just going to add these two numbers together, and that will give us the mass of FeS. So that's going to be 5585 plus 3207. There we go. That's going to give us 87.92 grams per mole. So we're going to use that as our molar mass to figure out how much product we would produce. And that's going to be 87.92 grams per mole. Moles are going to cancel. Times 0.122. Looks like a 10.7 grams of iron 2 sulfide would be produced. And this again is our theoretical yield. Now, again, If we wanted to figure out how much of our excess reagent was left over, so once again here, we want to know, and it wasn't asked necessary right here, how much of our excess left over. Once again, because we kind of chose right here, we already done the calculation. It's right here. We know from our calculation that we did earlier that we would need to use 0.122 moles of sulfur. And we know that we are starting with that many moles of sulfur. So we could very easily figure that out by taking 0.291 moles of sulfur, which is what we started with. From our limiting reagent calculation, we were able to figure out we needed to use 0.122 moles of sulfur. And that's how much we needed. And that means that left over at the end of this reaction, we should have 0.169 moles of sulfur left over. And if we want to know how many grams that would be, we could use the molar mass of sulfur at 3207 grams per mole sulfur. And 3207, about 5.42 grams left over. And again, here we started with 9.34 grams of sulfur. So roughly in this reaction, we used just under 4 grams of sulfur. Once again, because iron was our limiting reagent, we would have used 100% of iron up. All right, so again, that is the first approach that I showed you. And maybe here, maybe I could do it here. I think so. If you wanted to do the sort of other approach that we talked about, just to show you how to do that, I will again show you the other approach. And again, you can choose whichever way you like. So if we were going to do the other approach, obviously we would recognize that it is a limiting reagent problem. And we would do basically, once again, we would kind of just take our starting amounts here, and we would do 2 calculations to determine which one is our limiting reagent and how much we would produce. So we would take our one reagent and do a calculation from that reactant to our product, which is what we see here. We would then do a separate calculation starting with the other reactant, so 0.291 moles of sulfur. It is again a 1-to-1 relationship between these two. So we'll do our 1 mole of sulfur, gives us our 1 mole of our FeS, gives us 0.291 moles of FeS. Once again, here we can convert to grams by using the molar mass, and that's 8792, it looks like, per mole. And that would get us 0.291 times 87.92, gets us about 25.6 grams of FeS. So again, the other approach is 2 separate calculations, each starting with one reactant going to the product of interest. You would then compare how many grams each one would make. And as we can see here, the smallest number of grams made is our theoretical yield. And again, that would mean that this is our limiting reagent and this would be our excess reagent. The exact same determination, obviously, we may do in our first approach. So again, that's the other approach that you could do. Both perfectly fine. Once again, though, if you did this approach only, you would need to go back and do that calculation to figure out a question like this, how much of that excess reagent is left over. So again, would have to still kind of go back and do that other calculation if you were asked excess reagent. If you weren't, you would be done. Just put a circle around the smallest number, and that would be your theoretical yield and how much you produced. All right, so let's take a look here at some more here, I think, just to continue on. I think that was the excess part of it that we already did, so we're good on that. All right, so let's take a look at this one here. Here we go. All right, we got some molar masses given to us from the periodic table. That's 60 grams per mole here. If you had 622.7 grams of NH3 and you reacted it with 1241 grams of CO2, that should be CO2, it should be a small 2 there. We'll make it a small 2 now. There we go. Has a molar mass of 44.01 grams per mole. Which one's the limiting reagent? And calculate the mass of our product, which is the molar mass from the periodic table there. So actually you don't need anything other than what's in there. So you should be able to calculate it. So we're looking for how much product will be produced and which one's the limiting reagent, and I guess which one's the excess reagent. So take a few moments and see what you come up with here. And also how many grams of the excess reagent will be left over as well. I guess I should put that part in, huh? Okay, let's take a look here. So once again, obviously we know it's a limiting reagent problem because it's obviously asking about that and how much is left over. A reminder that it won't always ask you and tell you it's a limiting reagent problem. So how do we know it's a limiting reagent problem? So once again, when we look at it, I have grams of NH3. I have grams of CO2. That means that I can clearly get to moles of each reactant. And that's really how I know it's a limiting reagent problem. So once again, they won't always like give you that big hint of, hey, this is a limiting reagent type problem. So we want to start with the balanced equation, which we do. So that's good. We want to convert what they gave us into moles, and we want to do that. And they were nice enough to give us the molar mass of each of those things. If they didn't give us the molar mass, we would need to go to periodic table there and figure out the molar mass by adding up the parts. So I'm just going to convert these guys. So 622.7 grams of NH3. We're going to use the molar mass that was provided for us, but again, periodic table if it was not provided, grams per mole of NH3. I'll make sure to punch that in correctly here. So 622.7 divided by 17.03 going to give us 36.56 moles of NH3. We're going to do the same thing here for our other reactant. So we have 1,241 grams of CO2 using the molar mass from the periodic table of 4401. Going to give us 1241 divided by 4401 gives us 28.20 moles of CO2. Once again, we want to kind of label this as our starting amount of each of these guys. And because we do know that it is a limiting reagent problem, we're going to do our calculation. And in this case, I'm going to figure out how much, I'll go over here, how much CO2 is needed to use up all of my NH3 in this case. So I'm going to start out with my NH3, which is 36.56 moles of NH3. I'm going to do the mole to mole relationship between NH3, which is 2, and CO2, which is 1. So that's a 2 mole of NH3 from the equation to 1 mole of CO2. So 1 mole of CO2 up on top, 2 moles of NH3 on the bottom. Going to give us 36.56 divided by 2 gives us 18.28 moles of CO2 is needed. So again, this is the point where we're going to figure out which one's the limiting reagent. We're going to compare how much we need of CO2, which is 18.28, to how much moles of CO2 we are starting with, which is 20.2. And we could hopefully clearly see from that that I do have enough. And once again, because I do have enough, that means that the CO2 is going to be my excess reagent. The NH3 by default will then be my limiting reagent, and really kind of the important guy here, because that's going to be how much product we're going to make. So now that we determine which one's our limiting reagent, we're going to take the starting amount of our limiting reagent and figure out how much product we made. So we'll go with 0. No, that's not 0. That's a 3. Huh? Try that again. So, get something right with. There we go. So we're going to take 36.56 moles of NH3. We're now going to do the mole-to-mole relationship between our limiting reagent and our product that we're interested in. So again, we're going to do that relationship, and we can see for every 2 moles of NH3, we have 1 mole of our product. So we're going to go moles of our product up on top because that's what we're looking to end with. Moles of our limiting reagent on the bottom, which is 2. And that's going to give us 36.56 divided by 2, 1828 moles of our product here. And by the way, this answer right here would be our theoretical yield in moles of our product. We're not interested in moles of our product, though. We do want grams. So we do have to do that 4th step, which is use the molar mass to convert our moles to grams. We once again are lucky they gave us the number, so we don't have to calculate it. So to do that final step, 18.28 moles of our product. And once again, using the molar mass, which if it was not given to you, you would go to the periodic table to get it. Looks like it's going to be 60.06 grams per mole of our molar mass. And that will get us 18.28 times 60.06. Going to give us a 1,098 grams of our product. And now we could kind of think about significant figures, perhaps. Really looks like 4 significant figures on everybody. So this looks like a good answer right there. And that again is going to be our theoretical yield of our product in grams based off of our limiting reagent. It is the same sort of 4 steps. We had a balanced equation. We converted to moles. We took the additional step to figure out our limiting reagent. We then did our limiting reagent to our product mole-to-mole relationship, which is step 3, and then our moles to some other unit, which is step 4. So again, same 4 steps with the additional step of our limiting reagent. We also, in this case, want to know how much of our excess reagent is left over. So once again, we did get lucky here. Based off of this calculation, we actually figured out how much of our excess reagent we would need to use. So we can now very easily figure that answer out, which is excess left over. We know we started with 28.20 moles of it. That's how much we started with. And by the way, as we also know, our excess reagent is CO2, right? We figured out from our calculation, figuring out the limiting reagent, that we need 18.28 moles of it. Which if we subtract those two, 28.2 minus 18.28, that's a 992 moles needed. Moles of our CO2 is left over. And once again, if we want to know how many grams, that would be molar mass there of CO2 that we already have up on top. We'll times it by 4401. And that's going to give us about 436.6. I'll go up here. 436.6 grams of CO2 is left over. A reminder that we started with about 1,241 grams of CO2. So in this case, we actually use a good amount of grams, just under 800 grams of CO2 in this reaction. So once again, may not always tell you, and in most cases will not tell you it's a limiting reagent problem. Knowing that you have starting amounts of both reactants and able to get the moles of both of them, that is your key. That is a limiting reagent problem. All right, let's continue on here and see what we got up next. So now that we talked about sort of limiting reagent problems, and we've also talked about basic stoichiometry problems, and we've kind of touched a little bit about yields of reactions. Let's talk about officially what a yield of a reaction. By the way, a yield has to be a product. And that is basically what you get as a result of a chemical reaction. So when everybody says anything that's a yield, should be a product that we're talking about, and it should be a product that you're calculating how much you would produce. So there's a few different types of yields, and let's talk about these different types of yields and some of the differences between them. The yield of a reaction, as I mentioned, is a product and how much product that you produce. The theoretical yield, which is sort of what we've been calculating, the theoretical yield is the maximum amount of product that you should produce in a chemical reaction. Frankly, if everything went perfectly, there was no side reactions, I might have said it before, you weren't a klutz, you dropped anything on the ground, didn't leave anything over. If everything was perfect, which it never is, by the way, when you do it in real life, it never is perfect. But if everything was perfect based on the equation, based on how much you're starting with, the theoretical yield is your maximum amount of product that you should be able to produce. The theoretical yield, as we talked about, is always based off of the limiting reagent, right? Because that is the one that prevents you from making any more product once it's gone. So it's always based off the limiting reagent is where your theoretical yield's based off of. And again, as we talked about in a basic stoichiometry problem, it's assumed that whatever they gave you is the limiting reagent. So when you calculate a yield in a basic stoichiometry problem, whatever you started with is your limiting reagent. So that's why it works out okay in that. The actual yield is frankly what you would actually get or actually produce when you did this reaction, say in the laboratory or something like that, is what you actually did produce. Usually your actual yield should be smaller than your theoretical yield if you frankly didn't screw up at the reaction. So actually is what you actually produced. Theoretically is what you calculated. In actual problems, this is typically something that you will have to calculate. The actual yield is typically given to you in the actual problem. So somewhere along the way, they'll say, hey, you produced 40 grams of this product or something like that. So the good news in sort of textbook problems is the actual yield will be given to you. Most often you will have to still calculate the theoretical yield. And it will either be a basic stoichiometry problem like we did in the previous lecture, or it will be a limiting reagent stoichiometry problem. But those two ways will be basically how you would calculate the theoretical yield based off the equation, and essentially the same 4 steps that we've been talking about. Now, when you put both of those yields together, you get kind of an important yield that we oftentimes deal with, which is the percent yield. And the percent yield is taking the actual yield divided by the theoretical yield and times it by 100. So when you calculate percent yield, close to 100% is good. So higher percent yield is good. Low percent yield means you did not do so well in that reaction. Now, close to 100%, 90, 95, 98%, really good yield. Over 100% yield, could it happen? The answer is yes, it can happen. The other answer is not usually a good thing. So if you get over 100% yield, most often you probably screwed up somewhere. You really shouldn't, in a real situation, get over 100% yield. Usually means some type of error happened. For example, a very common error that could happen is, for example, if you made a precipitate through a precipitation reaction and you mixed all these solutions together, you made this solid that formed. You do a nice, wonderful filtration where you pour it through. You have your filter paper, that has your solid on it. And perhaps you weighed your filter paper first, and then you did this reaction. Let's just say, for example, you did not wait for this filter paper to actually dry or your solid to dry. What that means is you have a lot of water weight still on your filter paper, still maybe on your salt. And when you go reweigh it, you're going to have a much higher mass than you actually should. And that's because you have all this excess water that should not be there. That's actually an error. And you will get something, for example, like over 100% yield. And again, over 100%, not necessarily always a good thing. And this is a situation where it would not be a good thing. So ideally, a really good percent yield is a high number. close to 100, but not over 100, because frankly, that usually means that something error wise that you did. So for example, if you did this experiment with the precipitation, you would take that filter paper, you would put it in a drying oven and dry it out to get rid of all the excess moisture and water that's in there, or let it dry for a few days. And once it completely dries, when you reweigh it, you will actually see your actual yield should be less than your theoretical yield, because you won't have all that error of water weight that's on there. So that's a very common place in the laboratory where people can get over 100% yield, is like they do some type of reaction like this, and they just don't really wait for that water to dry out or that salt to dry out, and they have all that excess water weight. So let's take a look here at an example. All right, so why don't you take a try out this one here. We got this equation. We're going to start with 2.46 times 10 to the 4 kilograms of TiCl4. Molar mass also given to you, so you don't have to worry about it. 189.7 grams per mole. Reacts with 1.44 times 10 to the 4 kilograms of magnesium. Molar mass 24.31 grams per mole. How much is the theoretical yield of Ti in kilograms? And calculate the percent yield if we actually made 5.42 times 10 to the 3 kilograms. We get a little molar mass there for Ti is, we'll go 4788. Why not? Ti 4788. All right, so take a few moments, see what you come up with, and then we will discuss. Okay, let's take a look here. So once again, we were given kilograms here of one reactant. We're given kilograms of the other reactant. Although they're in kilograms, we could take kilograms to grams, and we could take grams to moles using the molar mass, which was also nicely provided for us. Not always the case. So what does that tell us is, technically speaking, I could get the moles of this guy. I could get the moles of this guy. So right there, that is the big blinking light that tells you this is a limiting reagent problem. So the key is, can you get the moles of each reactant? And if the answer is yes, you need to figure out that limiting reagent. So that's a very key thing to keep in mind as you come across stoichiometry problems. So remember that pretty much the first steps are the same regardless here of what we're doing. We want a balanced equation, so it is balanced. We want to take whatever they gave us and convert them into moles. So in this particular case, we are given in kilograms, so we do have to do an additional conversion, and that sometimes happens. You may be given starting amounts in all kinds of units, but the goal is to take whatever units they give you, get them to grams, and ultimately get them to moles. That is sort of where you want to end up here. So I'm going to start with the first one, which is 2.46 times 10 to the 4 kilograms. Now I'm going to convert this to grams, and remember that in 1 kilogram, there are 1,000 grams. So if I did that, that will convert my kilograms to grams, and this is TiCl4. At this point, I could use the molar mass, and you could get an answer if you wanted to, but I'm just going to continue on. And grams are on top, so grams need to go on the bottom here. And we're going to use the molar mass that was provided to us. And again, if it was not, you're going to go to the periodic table and calculate it yourself. And if we do all that there, 2.46 to the 4th times 1,000 divided by 189.7. And that's going to give me, and I'm going to go a little scientific notation on this, and we've got some big numbers. I'm going to call it 30 times 10. Looks like 1, 2, 3, 4. We'll try again. 1, 2, 3, 4, 5. Moles of TiCl4. I'm going to do the exact same thing with my second reactant, which is magnesium. Going to take the 1.44 times 10 to the 4th. Once again, I'm going to convert it to grams first. So that's going to be my 1 kilogram is 1,000 grams. Once again, you could get an answer, but I'm going to use the molar mass that was provided to get me all the way to moles. And that's going to be 2431 with the grams on the bottom, so they cancel. Moles of magnesium up on top. Grams cancel. Kilograms cancel. and that will give me 1.44. Make sure you're using, again, your exponent button when you do this, times 1,000 divided by 2431. Going to give me 5.92 times 10, count some decimals, 1, 2, 3, 4, 5 as well, moles of magnesium. Once again, this is going to be my starting amount. Since it is a limiting reagent problem, once again, I'm going to pick one of the reactants and figure out how much of the other one is needed. So here I'm going to figure out how much magnesium is needed. And again, what I'm figuring out is how much magnesium is needed to use up all of my TiCl4 in this case. So I'm going to start with my TiCl4, 1.30 times 10 to the 5th moles of TiCl4. It is a 1 mole to 2 mole relationship from the equation. So 1 mole of TiCl4 gives us 2 moles of magnesium. Once again, those numbers are, again, just the coefficients as we've been doing all along. We're going to do this, and this is going to tell me how many moles of magnesium I need. 2 moles of magnesium, 1 mole TiCl4. That's going to give me 1.3, again, making sure you use the exponent button, times 2. Going to give me 2.60 times 10. 1, 2, 3, 4, 5 moles of magnesium is needed. So once again, I'm going to compare the moles of magnesium needed to the moles of magnesium I'm starting with. And if I'm looking at the numbers are correct, we do have enough. Do have enough would be good. And that means here that the magnesium is our excess reagent and the TiCl4 is our limiting reagent. So once again, that's a really important part that you need to figure out. Again, calculation wise, you need to figure that out. And now that we do, we want to go back to our limiting reagent. And in this case, again, it is the TiCl4. And we want to make sure that we use the starting amount to figure out how much product we're going to make. So to figure out how much product, we're going to go back to our starting amount of our limiting reagent. We're now going to do the mole-to-mole relationship between our limiting reagent and the product, which are these two right here. And we could see that for every 1 mole of TiCl4, we get 1 mole of Ti. So here we will do our mole-to-mole relationship. 1 mole of TiCl4 gives us 1 mole of Ti. I could get an answer. It's going to be the same number, just to not have to write it again. I'm going to cancel out the moles, and I can continue on in this case because I'm looking for grams. Actually, looking for kilograms. So I'm going to use the molar mass of Ti that I have from the periodic table, and that's going to be 47.88 grams per mole. The moles will cancel. If I wanted grams, I would get an answer at this point, but if you remember, we wanted to know it in kilograms. So we do need to do one more conversion. And again, there are 1,000 grams in a kilogram. Now we are finally at the right units that we're looking for. And we're going to take 1.3 to the 5th. It times it by 47.88. Gonna divide it by, it looks like 1,000. Gonna give us, I feel like I hit the wrong number. I'm gonna try this one more time here. 1.3 to the 5th. And we are going to times it by 47.88. We're going to divide by 1,000. Gonna give us 6.22 times 10 to the 123 kilograms here of our product, which is Ti, would be our theoretical yield. All right, so there we go. I do have the number there, but I kind of scribbled over it. All right, so that's our theoretical yield. In the original problem, which is right about here, it does tell us that we actually produced, it looks like it's 5.42 times 10 to the 3 kilograms of TI. All right, so now that I got that number up there, our actual yield is there. So now we have everything that we need to calculate our percent yield. So our percent yield is going to be our actual divided by our theoretical times 100%. So actual was given to us, which it typically always is. And that's what that 5.42 number was. So we're going to take 5.42 times 10 to the 3 kilograms divided by our theoretical, which should be larger. That's good in this case. Everything went good, and times it by 100%. And that's going to give us a theoretical yield of, again, make sure you use your exponent buttons here, times it by 100. How about an 8714? Not too bad in terms of your yield, pretty decent. Yield here. Now, in terms of the percent yield, sometimes people have this question. So just clarify, since we're looking at it here, unit wise, it doesn't matter when you are doing your actual divided by your theoretical, as long as they're the same unit. So you could divide grams divided by grams if you're doing percent yield. You could actually do moles divided by moles. You could do, as we did here, kilograms divided by kilograms. As long as the actual yield and the theoretical yield are both in the same units, you could actually do any unit you want as long as they are the same. All right, let's try one more here, I think, to wrap it up this chapter. See how you do. Whoops, there it is. All right, so why don't you give this one a go here. 100 grams of ammonia is reacted with 100 grams carbon dioxide, and we do produce 120 grams of NH22CO. What is the percent yield? By the way, I think saw this one earlier, but I'll put up some numbers here to help you in case you don't want to reference back. 1401 for nitrogen, hydrogen 1.008, carbon 12.01, oxygen 16. All right, take a few moments and see what you come up with here. Okay, so to finish out this one here, I got 100 grams of ammonia, which is this guy, and I got 100 grams of CO2, which is that guy, and I'm actually producing 120 grams of this guy here. That, by the way, is going to be our actual yield as it was given to us. We're looking for our percent yield, which is our actual divided by our theoretical times 100%. And that appears we have our actual. So we do need to figure out the theoretical, doing some stoichiometry. We also know that I have grams of this guy and grams of that guy, which means I very easily could go from grams to moles of each of those. And that is the key. I could get the moles of each of my starting reactants. So our good thing of a limiting reagent problem we are dealing with. So we need to do a limiting reagent problem here to figure out the theoretical yield. Then we could actually calculate the percent yield. So equation balanced, done. What they gave us convert to moles. We will need some molar mass. If you reference the previous problem, if you didn't, we could calculate it here. So we got 1401 for our nitrogen. We have 3 times 1.008 for our hydrogens, which obviously comes from the periodic table. And that's going to give us 1703 grams per mole. We also need CO2. So that's going to be 12.01 for the carbon, plus 2 times 16 for the oxygens, going to give us 4401. And by the way, since our theoretical yield is in grams, we're probably going to need the molar mass of this guy as well. So while we're calculating, why not just do them all? NH22CO. So there are 2 nitrogens at 1401 plus 4 hydrogens at 1.008 plus carbon at 12.01 and an oxygen at 16. Okay, that's everybody. That's going to get us a, looks like 6006. All right, so I think now we got everybody that we need, probably for numbers. Okay, so we need to convert our grams into moles. So we can get rid of some of this, have a little bit more room. So we have 100 grams of each reactant. So 100 grams of NH3. Using the molar mass of NH3, again, to get rid of grams on the bottom. That's going to give us here 100 divided by 1703, 5.872 moles of NH3. We're going to do the same thing for our CO2. So we got 100 grams of CO2 divided by 4401 grams per mole of CO2. And give us 100 divided by 4401 gives us 2.7, not 7. There is a 7, but not there. So let's try it again. There we go. 2.272 sounds good. Moles of CO2. This again is going to be our starting amount of each of these reactants. So remember, because it's a limiting reagent, if we do the method here, we're going to figure out how much of one reactant we need to use up the other. So I'm going to figure out how much CO2 is needed, basically to use up all of my NH3. So I'm going to take the moles of my NH3, which is what I want to use up. And I'm going to do the mole to mole relationship from the equation between NH3 and CO2. And I see it is a 2 moles of NH3 gives me 1 mole of CO2. Once again, just the coefficients. So we're going to use that as a conversion factor. 2 moles of NH3 on the bottom. 1 mole there of CO2 up on top. Moles of NH3 is going to cancel, and that's going to give me 5.872 divided by 2. 2.936 moles of CO2 is needed. All right, in this case, we're going to compare how many moles of CO2 which is needed to how many moles of CO2 we start with. And in this case, it looks like not a good deal in the case of CO2. We need 2.9. We have about 2.2. Do not have enough. So that means in this case, because we do not have enough, the CO2 is going to be our limiting reagent. And by default, the NH3 here would be our excess. So here's a good demonstration that not always will you have enough. So in this case, we do not have enough, and that means our CO2s are limiting. So what that means is to figure out how much product we're going to produce, which is our limiting, which is our theoretical yield, we do need to actually start with our limiting reagent. So we're going to start with the starting amount of our limiting reagent. Again, important not to use this number. We want to make sure we go back to our starting amount because that's how much we actually are starting with. What we calculate here would be how much we would need of CO2 to use up the NH3. Not going to work in this case. So got to go back to the starting amount always when you're trying to figure out how much product. So once again, always go back to that starting amount of your limiting reagent here. So we're going to go with 2.272 moles of CO2. We're now going to do moles of our limiting reagent, 2 moles of our product, which as we can see here is a 1-to-1 relationship. So 1 mole of CO2 gives us 1 mole of our product. So we'll use that as our conversion factor. 1 mole of CO2, 1 mole of our product. Going to give us 2.272 moles of our product, which now we can convert into grams by using the molar mass that we calculated. By the way, you could also have just done this all in one step, without getting an answer in between. Perfectly fine. But since I kind of wrote it like this, I'll do it stepwise here. And that was 6006 we calculated earlier. And that comes from here that we calculated earlier. Grams of our product per mole. Moles will cancel, going to get us here then 2.7, keep putting that 7 first, 2.272 times 6006. That's 136. 136.5 grams of our product. And this would be our theoretical yield. Now, remember that we are looking for our percent yield. So now that we have all that theoretical calculated, and obviously our actual is given to us, and it's going to erase this, so somewhere to put it, and do it right about here, I think. Erasing action, there we go. All right, finish this out here, a little percent yield action now. We got our actual. We've taken our theoretical. We're going to times it by 100%. Actual given to us, 120 grams divided by our 136.5 grams times 100%. Once again, units are the same. So they do need to be the same. Don't always have to be grams. So like we did before, kilograms, kilograms, grams, grams. Can even do moles over moles as long as they're the same units. And we will get here 120 divided by 136.5 times it by 100, 87, it is 87.91%. Not too bad in terms of our percent yield. All right, so hopefully you're starting to see some patterns in these. It really is kind of the same 4 steps. If you see it's a linear reagent problem, which once again, you can clearly identify by having the ability to get to moles based on what they give you for both reactants. So that is the key to know that it's a linear reagent problem. I have information given to me about both reactants. I can get the moles of both reactants, linear reagent, which means balance equation, convert to moles, do that little calculation to figure out if you want to use up all of one reactant, how much of the other reactant you need. And once you figure out the linear reagent, once again, you always use a linear reagent to determine how much product you make, which in this case would be your theoretical yield. And then you can take your actual yield, which is given to you, divided by your theoretical yield, times it by 100% and get your percent yield. A reminder that the other way that we also talked about was, in just like in this case, you would have done 2 separate calculations, both starting with 100 grams of NH3 and figure out how much of your product you would make, then 100 grams of CO2 and figure out how much product you would make. Again, whichever one produced the smallest amount of product would be your limiting reagent and your theoretical yield, which would have been about 136 in this case, come out to the same number. And then obviously you could do your percent yield from that point. All right, that is stoichiometry for today here, I think. That should wrap up chapter 9, part 2. We basically all talked about limiting reagents, percent yield. So that should wrap up the entire chapter here with this one and the previous recording. So I guess all that's left to say is have a good one, and we'll see you into the next lecture after this one. And we'll see you soon, hopefully. Bye-bye.
Hello there, and welcome to the end of this lecture. Let me reach into my pocket and pull out the joke for you. What did silver say to gold when he tried to cut in line? Hey, you, get out of here. Bye-bye.